Hello everyone, welcome to this video. My name is Amir Sentinel1. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to do classification using machine learning approach in the Google Earth Engine platform. First of all, select your region of interest using administrative layer borders available in search places on dataset. For example, here, if you search for administrative layer unit, here you can see the first level and second layer data is available. The first layer corresponds to the province borders. Import it into the code. If you want to have a preview, map.add layer helps to get a preview about the table. Run a code, and now as you can see, all the provinces border, as you can see, highlighted in this layer. So I'm gonna select a province that I have a little information about the land covers, because when you want to do supervised classification and land cover mapping, it is important to have some initial information about the region of interest and type of land covers available there. For example, in Iran here, there is a province, as you can see, in the north of Iran. And as you can see here, we have different land covers, croplands. Let me to turn it off here. We have actually croplands, urban area, water bodies, forest, and also the rangelands available here. It's a good combination of different classes, and it's a good location to show how we can differentiate different classes using machine learning technique in the Google Earth Engine platform. So now I'm going to show you how to select the region of interest. As you can see, now actually the table included all provinces, but we want to have only this province that's covering or actually bounding our region of interest very well. Using marker tool available here, we can pick the region of interest like this, and then make a new variable as ROI equals to from the input table that filter bound. You can filter the shapefile based on the marker that is geometry. So then use map.centerObject ROI and map.add layer ROI. Run a code, and now you will see we have the border of target area. This is very simple technique. Instead of using clipping approach, here we filter our data because it was a feature collection. Now we filter the feature collection based on the feature that correspond to the geometry. So now if you get a print here, get a print ROI geometry, print ROI, the geometry shows how many vertices available in this layer. As it is a shapefile, it is actually the complexity of shapefile or the figure of shapefile is very important for the further analysis. Large number of vertices could reduce the speed of processing. That's why we need to do some sort of simplification to actually keep the main border with the lower vertices. That's why here I need to make a function first using map. The input for the function is a feature, and finally function returning the input feature that is simplified. So the simplification has actually the maximum error. A larger maximum error, lower vertices. For example, I'm gonna have 1000 maximum error here. And now as you can see, the figure of region or the border is highly simplified, and also the number of vertices reduced to 100 instead of 400. Now it is better for the processing, specifically in the Google Earth Engine platform. It is very important to reduce the size of shapefiles using simplification for the further analysis, specifically when you are dealing with machine learning approach here. So remember to save your code, and then I'm gonna call Sentinel2 and Sentinel1 images for the classification approach. As you know, before go through the classification process, we need to have actually a diverse set of satellite data in different reflectance, in different characteristics that highlights the different land covers over the region of interest. For example, the reflectance bands, the radar bands, and also the spectral indices could be a good combination of satellite data that you can use for the classification approach. So actually, the higher variety of data set, the higher variety of bands and images and indices, most of the time helping you to get a better result in the classification approach. So now I'm gonna call Sentinel2 images for 1 year. So here, go to search places and dataset, type for Sentinel2. Sentinel2 level 2A here is available, and you can import it into the code as an image collection. Then assign image collection to the Sentinel2 and filter its collection based on the year and region of interest. For example, I'm gonna make a land cover layer for 2023, starting from 2023 and ends to 2024. Then I'm gonna bound our data or filter our data based on region of interest, that is ROI. It is very important part because maybe a region of interest including different types of the Sentinel. That's why we need to filter to call all Sentinel2 frames that's covering or passing through the region of interest. So then I need to make a print from Sentinel2. In the right panel, you can see here we have an image collection. After a few moments, 900 image collection is available here. But if you go to the properties, you will see we can actually define the other filters to actually reduce the number of images, because I want to have higher accuracy and lower inaccuracy in the process. That is very important to remove or get rid of images including high cloud cover. So as you can see here, cloudy pixel over land percentage. This is a good parameter helping us to actually filter our images based on the amount of cloud cover over the land, because the region of interest totally corresponds to the land, and also we don't have sea here in the region. That's why we need to make a filter based on the cloudy pixel over the land. So for example, I'm gonna call those of data in which cloud cover is less than 10%. So to have a collection of, for example, clear images. So the filter earthengine.filter.lt less than filter based on cloudy pixel property. I'm actually the less than filter helps to call those of images in which cloud cover over the land is less than 10%. Run the code again, and in the right panel you will see only 200 images left here for the further analysis in which cloud cover is less than 10%. It is very, very important part here. So if you go to the bands, you will see a couple of bands available here, starting from band number 1 to band number 12, and also there are some extra bands here that is not necessary to have for the classification process, but only some of the bands such as band number 2, 3, 4, 5, and 8 could be enough for the classification approach, because we want to have the main bands or uncorrelated bands to highlight the main land covers in the classification approach. That's why we need to make a loop to select the target band and apply the scale factor and calculate the NDVI or other spectral indices that is necessary for this area. So here, let's map. First, make a loop structure using that map. Then a new function defined here, input images called as an ing, or you can choose any other names that you want. Make a new variable as a bands here in which from each input image that is already named as an ing, I'm gonna select bands starting from 2 to bands number, for example, 8. It is a combination of visible and near infrared bands. So then that multiply help us to apply the scale factor here. If you go to the data properties, whenever you are working or dealing with satellite data in the Earth engine, you must go to the data description and check some of the potential scale and offset that might be available for that satellite data. Before further processing, it is necessary to apply the existing scale or the offset value on the data. As you can see, we have a scale. We have a same scale value that should be multiplied on each band. Go to the data, go to the code, and here multiplied to the scale value. Then another variable as NDVI defined here, because the NDVI is one of the suitable indices to differentiate water, soil, and also the vegetation cover. NDVI equals to, from NDVI image, actually from bands that is already corrected. Now bring the bands here and then get the normalized relationship between normalized difference between band number 8 here, as you can see, band number 8 as a near infrared and band number 4 as the red band. And also here we can have other indices such as NDWI that helps to detect the water content and the water surfaces. So here again I will have a band dot normalized difference. Here I'm gonna get a relationship between band number 3 green and near infrared, band number 8, just like that, and rename them as first one NDVI and the second one as NDWI, just like that. So NDVI, NDWI, and also the multispectral band in visible and near infrared region selected here. And now we can return the function as a data set that's including all these bands. So here, returning the bands that add bands with NDVI in each date and also the NDWI for each date through the add bands. NDWI, just like that. Then copy the properties from input images to the output. As we mentioned earlier, each image has a couple of properties here that should be available for the further analysis. For example, and also among the existing parameters here, only system time start and system time end is necessary. Let's make a bracket like this and enter system time start and system time end. So there it is. A new image collection is created, same number of images returned, and also if you go to the features, we have only 9 bands available here, starting from B2 to band number 8, and also with NDVI and NDWI calculated. So now I need to calculate the percentile for the Sentinel2. The percentile of each image should be calculated to explain the temporal variations of land covers such as vegetation cover, croplands, and forests and water bodies. That's actually facilitates the process of differentiating between classes for the classification purpose. And percentile technique is a suitable technique that helping us to make this process easier. So now here we have Sentinel2 percentile equals to Sentinel2 already included VNIR and also spectral indices such as NDVI and NDWI. Dot reduce Earth engine dot reducer dot percentile. So here you can actually calculate different percentile according to the data that you have. For example, I'm gonna get percentile with 80% percentile, or you can get a percentile, for example, 55. 55 is something like the median or the average, and also the 80 is something near to the maximum value. And also that these two kind of percentile help us to explain the temporal variations, specifically between the forest and also the croplands. It is very important. You can have also extra percentiles, for example, such as 70. This is another percentile that we can have to explain the variations better. So here, for example, we will calculate the percentile 90, 70, and 55 here, and through the map.app layer, I can highlight the output. I can visualize the output that here is Sentinel2 percentile that is clipped based on the region of interest. The region of interest is ROI. The geometry is the only marked region. When you get the percentile, the output will be mosaic because for each pixel available in the actually all frames available for each date, their percentile in 90%, 70%, or 55% calculated, and this calculation make a mosaic layer of different percentile values. So here we have Sentinel2 collection, and then we will have a false that avoid automatic visualization that helps to keep the speed of processing in the Earth engine. Remember to save your code and run it again. After a few moments, you can turn the geometry off, and here the Sentinel2 data is available. First, I'm gonna make a visualization from percentile image here. First, from the visible and near infrared band, a combination of, for example, 90%, for example, 70, I'm gonna make a combination of 70% from band 8, 70% band 8, 70% band 4, and also percentile 70 for band 3, just to show the visual characteristic of region of interest here. After a few moments here, you can see the actually this is the a false color composite of region of interest. Or you can only have two kind of percentile to reduce the impact of clouds or snow covers, as here it is a mountainous region sometimes covered by the cloud, and you will see. Or you can see the variations of NDVI or NDWI here through a one single band. This is NDVI 55 that is close to the average NDVI for the whole region of interest. This is NDWI 90% or percentile 90. That is close to the maximum NDVI value for the region of interest. Oh, this is NDWI actually. That's why the water bodies and also the snow cover highlighted in this region. If you want to avoid from the cloud cover, if you want to avoid from the snow cover, that's better to actually remove the NDWI. It's totally up to you what kind of actually land covers you want to highlight in the output. For example, if I remove the NDWI here, then we only have NDVI and visible near infrared bands. Over here, for example, we only have NDVI with 90%. That shows the close maximum value, not exactly the maximum value, the closest value to the maximum without considering some sort of extreme values. And this is NDVI 50%. Run a code again. This multi-temporal variation, specifically in the NDVI, help us to highlight the differences between croplands and also the forest area. That is one of the big challenges in the classification purpose. So again, with 55%, that is close to the average situation. Yes, there is. So, and then you can also reduce the number of percentiles. As I said, it is totally up to you. You can have only 75 and 55%, or you can have a multiple percentile values. And also it depends on the accuracy of output. If the accuracy of output was not good enough, then you can add the extra percentile value. Just here I want to limit it to the 2 percentile, 75 and 55. So the Sentinel2 data gets ready, and now I'm gonna call radar Sentinel1 images as a supplementary data for the classification purpose. Although the spectral characteristic in classification is very important, and also the spectral characteristic already provided by Sentinel2 data, but having radar data help us to differentiate the urban areas from the bare land. And also that would be a useful technique for separate the urban from non-urban region. Make a new variable as Sentinel1 here equals to, go to search places and dataset and type for Sentinel1. As you can see, SAR data available here, imported as a second image collection. So here assigning the second image collection to Sentinel1, the second one, and then filter it based on the year first, 2023, and then filter it based on the region of interest. The region of interest here is ROI. And then there are some necessary filters specifically used for the Sentinel1 data here. One of them is list contain filters for one of the properties, EarthEngine.filter.list contains. As you can see here, let me to show you something before you want to define extra filters for the Sentinel1 data. It is important to know what kind of properties we have here. Let me to print from the first Sentinel1 data just to highlight something about their properties. For example, here we have one Sentinel1 data. If you go to the bands, you will see a combination of VV, VH, and angle. The VV, VH shows the direction of electromagnetic radiation traveling toward the target and also receiving by the sensors. For example, V means vertical and H means horizontal. The V means the first V show meaning that the wave actually the electromagnetic radiation goes vertically toward the target and then back scattered toward the sky, vertically and horizontally. In the first band, as you can see, only the vertical backscatter received, and also in the second band, the horizontal backscatter received. This is the direction of wavelengths, actually, or the waves we are working when we are dealing with the microwave region. So So VV means vertically sent and vertically received, and VH means vertically sent and horizontally received. And most of the time, we prefer to use a VV for the analysis because provided more radiation and more energy and more accuracy for the estimations. But however, combining VV and VH together help us to discriminate the differences in the radar data that could be suitable for a classification purpose. But you don't need to angle. This is the angle of scattering that should be removed for the further analysis. I will show you how to do it in the next step. So then in the properties, if you go to the properties here, we have a metadata including different information about the data. And also according to the metadata we have here, we must define some sort of filters. For example, one of the filters is least contain. So we want to make a least contain filter according to transmitter receiver polarization. So transmitter receiver polarization equal to or least contains. From the list of properties, I'm gonna have those of data in which transmitter receiver polarization R, S, and T, here it is, contains VV. VV is very important for us. Here contain VV and VH, no matter, but having VV is necessary. So then I'm gonna have another filter based on the properties we have here, Earth engine that filter that's equal. So the equal filter goes for instrument mode. So here the instrument mode should be interferometric wets or IW. Here, as you can see, instrument mode is another properties we have here that equals the IW, just like that. And now, if you print the result in the right panel, you will see 329 SAR data is available for this period of time. So the next step, we want to select the target bands here. That select VV and VH. We want to have both bands together and skip the angles. And another properties that must be considered is the orbit properties pass. The SAR data taking in two geometry style, one of them descending and another one the ascending. And the angle of actually the imagery angle or the image incident angle in the descending and ascending image is different. Actually, the ascending and descending images, both of them capturing image from a same region but from two different sides. For example, ascending take images from the right side of the feature and ascending take picture from the left side of the feature, or vice versa. This is the geometrical difference between ascending and descending image. That's why we cannot have ascending and descending mode together in a same collection. It would be better to have one of them, and also in some of the applications we will have both but in two different variables. But here I prefer to have one of them, descending mode or ascending mode. So if you want to see how many data available in the ascending or descending mode, here you can test it using the print. Here aggregate array is a function that shows you the frequency of the properties. For example, I'm gonna see the orbit properties pass. Orbit properties pass, here it is ascending, for example, first. In the right side, ascending is wrong. So the arguments aggregate array, orbit properties, just orbit properties. I think, yes, now it works. As you can see, some of them are ascending and some of them descending, but it seems the frequency of descending is more than the ascending images. That's why I prefer to make an equal filter according to descending mode. Earth engine dot filter dot equal, so orbit properties pass will equal to descending mode. Finally, print Sentinel1 data to see how many images we have. As you can see, 200 images available in descending mode, and now we can calculate the percentile 75 and 55 for Sentinel1 images. That is very useful to explain the temporal variations of vegetation cover in the SOAR data. So here, do the Sentinel percentile process, this time for Sentinel1 data. Sentinel1 percentile equals to Sentinel1.reduce Earth engine.reducer.percentile. Just like that, 75 and 55. Print Sentinel1 percentile. In the right panel, you will see one image including 4 bands. And also we will have percentile 75 and 55 for VV and VH mode. And also we can have another map.add layer, this time for the radar data, to have a preview about the radar data characteristic. So Sentinel1, and here it is Sentinel1. Remember to save your code. In the right panel, the layers available, but I want to see VV75, click on apply, check it on. So here it is. As you can see, the water bodies shows the lowest reflectance value because the microwave region is highly sensitive to the topographical or roughness or surface roughness. As you can see in the mountainous region, as much as roughness increases, the amount of reflectance value also increases. The water is very smooth, and also then the backscatter is very low or small, and also the urban area or residential area has roughness structure, has a rough surface. That's why you can see the higher backscatter value for the urban area. That's why the radar data is one of the best options to highlight the urban infrastructures or urban buildings in the classification process, specifically for arid and semi-arid region. So this area urban covered by the vegetation cover, and we don't have a big problem to differentiate the urban and also surrounded region. But if you work on an arid and semi-arid region where the urban area covered by surrounded by bare land or exposed area, in that case you will face a lot of issues to differentiate the urban and also the bare land from each other. So here it is, and then you can have a preview about VH band. Here you will see the value of scattering is very low compared to the VV, because when we have the same polarization in sending and receiving radiations, more electromagnetic is available, then the quality of image will be higher compared to different polarization for sending and receiving. So there it is. And now I'm gonna make a single data set including Sentinel2 and Sentinel1 images. So here data set equals to Sentinel2 dot add bands Sentinel2 percentile images that add bands to Sentinel1 percentile. If you get a print here, you will have a dataset including Sentinel1 and 2 for the region of interest. Here it is, 20 bands available, including visible near-infrared bands, spectral indices, and also the radar data. It is a good combination for the land cover mapping for all around the world. It is also, it should be noted that this tutorial can be used for all around the world, not only limited to one specific regions. All the data, shapefiles, layers, everything is available globally, and you can use this method for all around the world for any regions you are working. So remember to your code, and now we want to actually take some samples from different regions for the classification purpose. First of all, I'm gonna make a false color composite from the region of interest. So turn Sentinel2 on and go to the 3 bands RGB and make, for example, band visualization from, for example, near infrared, red, and green. Totally, for example, here the percentile 55, it is reflecting an average situation, the average reflectance value during the time period, and it could be a good option for the visualization because we want to have a visual view of region of interest to collect our samples. So, for example, here band 8 selected first. So we are actually giving band 8 to the red band, and then I'm giving band number 4 to the green color here, and it should be 55, and 8, 55, and also band 3, 55 again. Increase the contrast by 90% value. After a few moments, the contrast increased, and now here you can see the the false color composite that shows the agricultural area, the forest, bare land, and other land covers. So now we need to select we need to make different feature collections for each classes. For example, here, as you can see, we know that here there are airband, water, cropland, forest, and also the bare land, because we can see them easily. Or if you cannot distinguish different classes, I'm suggesting you go to the satellite view and have a more zoom on your region of interest to get more understanding about the classes you have here. So after you get information about existing classes, then back to the satellite view and make sample or start sampling process for each class. New layer, first make a new layer, go to the properties, and here you must turn it to the feature collection. It is very important. The samples you use for classification must have feature collections nature. So the first class is, for example, water bodies, and the color class could be blue, and the property is very important. The property should be same for all classes with different values. So the property is class, or you can choose any other name. Just remember to use the same property for all samples. And then value is class number 0. Click on OK and go to the water bodies and take the samples here. So if you taking samples by a rectangle is easier. Now I'm trying to collect some samples using a rectangle tool or drawing tools available here. Here it is. Here we have 10 meter spatial resolution that is suitable for sampling process or land cover mapping. So again, collect some samples from the water bodies. So, and then go to for the next class, a new layer, and geometry, go to the geometry number 2. This is, for example, cropland, and color could be light green or something like that. Turn it to the feature collection. Again, property is same as class, but we have different value. Previous class was class number 0, and here we have class number 1. So here we have different different croplands. If you zoom in a little bit, you can find actually croplands available here, but the farmlands or croplands fields are too small or very dense region. This area is very dense and complicated, but you can find easily the red regions as a cropland here, and also as we already double checked with the high resolution Google image that we have access here. Go to the cropland and then turn it on, turn the image on. This is for Sentinel1, but we want to have Sentinel2 images. Try to take some samples from the croplands, just like that. And I recommend to take the samples from different regions, because maybe in different regions you have different crops and their NDVI behavior during the time will be different in that case. So here, for example, I'm gonna taking some samples from this area, just like that, and then go a little further or scroll more on the images to find a newer area that may have different NDVI behavior during the time. So as you can see in the high resolution view, it is obviously all the region covered by the croplands. So again, I go to the cropland class and take some samples from here, just like that. So now go for another class. This is, for example, forest, and I'm gonna see the samples with the dark green. It is a feature collection. The property is same, but the class value will be different. This is the third class. As classes started from 0, this is the third class, class number 2. So go to the forest region here in the elevated area. So for regions with higher elevation, we have the forest. So as you can see, the forest available here. Just you can take your samples using drawing tools or rectangle available here. It is very important to actually collect your samples from various regions, not only limited to one single location. Just like this. So the next class will be urban area. Go to the properties. Here it is, the urban area. The geometry will be feature collection. I'm gonna see the samples with the black color. The property is class and the value is number 3. Click on OK and go to the urban area and take the samples here. Select the urban and collect your samples. The urban area is a heterogeneous region, and it is a combination of impervious surface, vegetation cover, or even water bodies in some regions. That's why we need to have a Sentinel1 or radar data to highlight urban area as a clear or single class compared to the others. So as you can see, some areas highlighted with red among the buildings, but it is necessary to take enough samples from urban area to ensure that we can have it as a separate class next to the others. So again, go to the urban and take samples just like that. So next will be some rangelands we have in the upstream. These are not bare land or soil. These are actually some poor rangelands that we have in this region. Just make a little zoom on this area. As you can see in the high resolution data, it is clear that these are poor rangelands. So make a new class for the rangelands, go to the layer properties, turn it to the feature collection. The class name is rangeland. The class color could be, for example, orange or something like that. We will have class property, the same property, and the class value is 4. This is the class number 5, but the value is class number 4 because the origin starts from 0. So, and now select the rangeland using a rectangle tool, just taking some samples like this. So for here we have a lake, and now I'm gonna select some samples or pick some samples from the lake here easily. So for here we have another lake. Let me to take samples from here. If you want to remove a sample, it is easy to use edit tool here, select, delete, or make any change if you want. So now I have all the samples for all the classes. So in the next step, we need to merge them into a single variable. So for example, here a new variable as samples equals to. So here the class names available here: water, cropland, forest, urban, and rangeland. Water dot merge cropland dot merge forest again dot merge, just like this. Continue until from the first to the final classes. Forest, urban, and rangeland here. 1, 2, 3, 4, and 5 classes here we have. So all the samples collected. Now I want to make a relationship between samples and data set. Here I will have training data. The training data, in the training data, the algorithm, the target algorithm is from data set. Let me to write it first, and then I will explain what is going on here. Data set from sample regions. So the sample regions works like this. Making a relationship between samples and data sets, and the relationship means some cluster or initial cluster created for each classes based on their position in the feature space created by the data set. It's a little complicated. If you go through the theory of the classification process, definitely you can get a better understanding about its actually working. So sample regions, some of the arguments available here, some of the arguments available here. Some of them are necessary. For example, the first is the collection correspond to the samples already collected, and the next one is properties. The properties, as you remember, when I was collecting samples, all classes had the same property, that it was class. That's why the properties as class structure or class name, or the scale for the sampling. If you reduce, definitely if you set it to 10, because the spatial resolution of Sentinel2 data is 10 meter, definitely you will face with some sort of errors, such as user memory limit exceeded and so on. That's why I'm suggesting you to use, for example, lower values for a spatial resolution, such as 30 or even 100. So that highly helps you to run a code with a higher speed of processing, because nowadays the speed of processing is very, very necessary in the Earth engine. So, and another, the first one was samples, the second one training data. Once the initial clusters created, now I need to define the model classifier model here. So another variable model equals to, so Earth engine dot classifier, just like that, classifier dot small random forest. As you can see, various classifiers available here, and these are part of well-known machine learning algorithm for the classification purpose. But one of the best one and the most utilized version is a small random forest in the classification. Specifically, when you are dealing with vegetation cover, the random forest is one of the best methods among the machine learning classifiers for the classification purpose. You must set a number of trees here. Experimentally, I found 80 as a good option here, or you can use it in your work. And then the classifier should train based on the clusters created. So here, train help allows to do this process. Some of the arguments are necessary, such as a feature. The input feature is training data, and the class property equals to the class we mentioned earlier, and input properties equals to the dataset band names, just like that. So the model is also created. If you want to see if there is any problem in the model created or not, just print the model and then you will see there is a problem. Required argument features is mixed. Here, modify feature and run a code. Here, the classifier is under computing. Once the classifier created successfully, meaning that there is no problem in the training data, samples, and the model, then we can go for the classification purpose. So, as you can see, the gear is circling the classifier trained. So now we want to apply the model on the dataset to predict the potential class or anticipated class for different pixels according to the trained model. So here we will have a map here equals to get dataset first and then classify their pixels based on the trained model we had before, and rename it as classified map. So finally, through the map.add layer, visualize the output that is clipped based on the region of interest, that is ROI here. And here, the minimum value in the map is 0. The maximum value for classes is 4. And you can even define colors for different values. For example, the first class is water with blue. The second one, cropland, green, the third one forest, for example dark green, and the next one is urban area, black. The next is rangeland, I think, for example orange. The layer name is map, and use the false at the end to avoid automatic visualization. 1, 2, 3, 4, 5. 5 values, 5 color. So save the code and run it again. After a few moments, the map will be ready, and if you click it on, you will see the classified result for the region. Definitely takes a little bit longer. Here it is, but seems as something is wrong because the accuracy of classification is not good. Maybe something is wrong in the final results because the urban area classified very well, but as you can see, the croplands not actually classified very well, and most of these region covered by the cropland seems covered by the rangeland. That is wrong, and also we need to go through the code to see what the problem what was the problem that such kind of errors occurred. If you go to the inspector here, you can check the class values. For example, here the class value, if you go here in the map, classified map is class number 4. It is a rangeland, so it seems we have a problem for the croplands that we need to actually check something to see what was the problem that caused this kind of confusion in the output. When you face with such kind of errors in the classification purpose, suggesting you to modify the samples. For example, here the big problem related to the croplands, and I'm gonna try to add more samples for the cropland to see if problem solved or not. For example, turn it off and back to the samples here. For example, we want to have Sentinel2 data NDVI image that highlights the vegetation cover for the region of interest. 75% NDVI give us a good estimation about the vegetation cover in this area. Click on apply and check it on to see the NDVI variations over the cropland. If you want to see how to make some changes in the samples, I'm suggesting you to add more samples for the croplands. For example, try to take more samples from the left side of the regions, or the other regions that you didn't consider, that you haven't considered yet. And for example, here I'm trying to take samples for the croplands from these regions or these regions. Yeah, this could be a good method to fill the sample gaps, and I hope this actually extra samples helps to solve the issue. So run a code again and see how it works. Just we added some simple samples or extra samples to the cropland class, and now I'm waiting to see the result. Check it on map, and now waiting to see the new result. After a few moments, you will see the classified image for this region. If you had any syntax problem in the programming and also this tutorial, you can actually find the code link below this video on my YouTube channel. So as you can see now, the quality of output improved a lot just by adding some new samples. You can see the quality of estimations increased a lot, and most of the problems for the croplands removed. And definitely if you try for more samples and if you take more samples for all classes, definitely you can increase the accuracy of estimations much better and better. So, and if you want to save this output, or if you want to download the classified map and use it in your desktop software such as ArcGIS Pro, you can use export.image to drive. Most of people asking about how to download from Earth Engine, but as you can see, export.image to drive is the best way. Export.image to drive, as you can see, it is the best way to get outputs. The output is, for example, the map that is clipped based on the simplified ROI, and the description refers to the name of the output. For example, this is the map 2023, and the region of interest equals to the ROI. The scale for the output should be 30 meters because I have selected a very big region. If I choose, for example, 10, definitely I will face with user memory limit exceeded problem or something like that, or I will have different times for the output. That's why I prefer to set a lower grid size or grid actually structure for the output image. You can set a folder for the output. For example, I'm going to use the test folder, and also the CRS, the coordinate system for the output EPSG 4326. The next one is maximum pixels equals to 1E13. There it is. Save your code and run it again. In the right panel under console, here you will have a new output map 2023 ready to save in Google Drive. Just click on run and run again. After a few moments, the process of saving started, as you can see, and once the tab's color turned to the blue just like this, meaning that the data saved completely, and you can pick it up from your Google Drive and open it up into the desktop software. I hope you like this tutorial, and I really appreciate it for your attention.